Okay, so this problem is asking us to find all values of p so that y equals x to the power of p is a solution to the differential equation 3x dy dx equals y. Okay, so notice that we have y equals x to the p, and this means, of course, that dy dx equals px to the power of p minus 1 by the power rule for derivatives. Thus, if we want to find the values that are a solution to this differential equation, we would need to take, 3 times x times dy dx, which is px to the p minus 1, has to be equal to y, where y is x to the power of p. So therefore, let's see if we try to collect like terms here and simplify. Let's say I have x times x to the p minus 1, so this becomes 3p x to the p equals x to the p. And so if we need 3p x to the p to be equal to 1x to the p, this implies that 3p is equal to 1, and thus p must be equal to 1/3. So the solution to this problem is p equals 1/3. Next, find all values of capital B so that y equals radical bx plus 3 is the solution to this differential equation. So let me rewrite this as y equals bx plus 3 to the power of 1/2 so that it's easier for me to do a derivative and get dy dx by the power rule would be 1/2 bx plus 3 to the power of negative 1/2, and then of course by the chain rule we'd have to put a b in there as well. So this provides the dy dx as b over 2 bx plus 3 to the negative 1/2 power. And so when we bring it over to the differential equation dy dx, we would need b over 2 bx plus 3 to the power of negative 1/2 equals 5 over y, and y itself was the radical of bx plus 3. So therefore b over 2 bx plus 3 to the negative 1/2 would have to be equal to 5 bx plus 3 to the negative 1/2. And since those are equal, that would mean b over 2 would equal 5, and hence b equals 10. And that completes that problem. So now for our last one, let's try finding all the values of a that make y equals 7e to the ax a solution to this second derivative differential equation, right? The second derivative, second order differential equation, we would say. So y equals 7e to the x. The first derivative with respect to x would be 7e to the ax multiplied by a by the chain rule. I'm going to place that out in front. And then the second derivative with respect to x would be, let's see again, 7a e to the ax, and then multiply by another copy of a, so let me just put in a squared. So then when we come over to the differential equation needs d squared y dx squared, the second derivative, 7a squared e to the ax, to be equal to 9 times y. 9 times 7eax. So 7eax, 7eax, and that means we need a squared to be equal to 9, and thus a should be equal to plus or minus 3. Okay, here we're going to solve differential equations that contain x and y by using a method called the separation of variables, which effectively just means to literally separate the variables by moving the y's and the dy's on one side and the x's and the dx's on the other side. So we're going to treat dy over dx as if it were a fraction. So we're really technically thinking about the delta y and the delta x, right? The change in y and the change in x. But effectively, it just looks like you're multiplying. And then after that, we're going to integrate both sides and use an initial condition if there were one. So in problem number 1, we have dy dx equals 1 plus y squared over x squared. So for this particular problem, if we wish to solve, we would look at it as dy over 1 plus y squared equals x squared dx. So in other words, I'm moving the dx over to that side, and I'm dividing by the 1 plus y squared. Okay, after doing that, we can then integrate both sides. So the antiderivative of 1 over 1 plus y squared with respect to y would be an arctan of y, and the antiderivative of x squared would be x cubed over 3 plus a constant. Now technically there's a constant on both sides, but if I were to subtract one constant from one side to the other side, then a constant minus a constant is still a constant. So this is a fine way of writing it. Then solve for y explicitly as a function of x. Actually, most of the time this is considered to be a good enough solution to this differential equation, but if you did wish to, for example, isolate the y here, we don't have an initial condition, so I can't do that. But if I did the tangent of both sides, we'd get y equals the tangent of x cubed over 3 plus a constant. And so that would be the way that we might perform this problem with no given initial condition. Okay, so moving on, if we want to try this one, dy dx minus 4xy equals 0. As a first step on that problem, let's add 4xy to both sides. So the dy dx equals 4xy. Then I will divide the y, and I'll multiply the dx. So now I have dy over y equals 4x dx. Integrate both sides. Logarithm y equals 2x squared plus a constant. And so if we wish to isolate the y, again, I would raise e to the on both sides and get y equals e to the 2x squared plus c. Now, from now on, I will always write this in a different way. I'll always write this as e to the 2x squared multiplied by e to the c, because addition in the exponent means product with the same base. And then since e is a constant raised to a constant power is also a constant. So my final rewrite will be to write it like this. So again, whenever I get this e blah plus c, I'm always going to write a constant out in front instead of that particular constant e to the c. It'll be easier to solve for in initial condition problems. Okay. In the third problem, dy by dx plus 3y equals to 0. So now dy dx equals negative 3y. So dy over y equals negative 3 dx. And thus, the log of y is equal to negative 3x plus a constant. So if I were again going to raise both sides to the e power, for this one I would end up saying y equals e to the negative 3x, but as mentioned in that last part, that plus c just becomes another constant that I can replace out in front. So that's what I'd be getting for this one. For problem number 4, we now have dy dx equals x squared y, and thus dy over y is equal to x squared dx. And so when we integrate, we're going to end up getting ln of y equals x cubed over 3 plus a constant. All right. Coming up to here, that means that if I were to raise both sides e to the, we would end up getting y equals, let's see, e to the x cubed over 3, and by our little trick again, multiplied by a constant. That's what that plus c ends up meaning. This time, though, we were given an initial condition, right? We were given this condition. So if I were to replace x with 0, e to the 0 cubed over 3, that means that the output must be negative 2. And notice the convenience now of writing that constant out in front. E to the 0 is just 1, so negative 2 equals c. And that means as our final answer, we can write our answer as y equals the c that we just solved for, e to the x cubed over 3. And that completes this problem. So now on to problem number 5. On problem number 5, we see 2 plus 2y squared dy dx equals e to the x multiplied by y. Okay, lots of variables to isolate here. So we'd have 2 plus 2y squared. We'd have a dy, and then that y would be divided over. And then over here we'd have e to the x dx. Notice on the left-hand side, this is equivalent to 2 over y plus 2y, dividing the y through on the 2 plus 2y squared dy, and that's equal to e to the x dx. So now if we integrate, the integral of 2 over y is 2 times the ln of y plus y squared equals antiderivative of e to the x is e to the x, and then don't forget our constant. So in this case, I would not be isolating y because I don't have a good effective way of separating the y squared from the logarithm of y. Okay, on the next page, last problem on the last page. Find the equation of the curve y equals f of x that passes through 1, negative 1, and whose tangent line at the point xy is perpendicular to the line through xy with slope negative 2y over 3x squared. Wow! Okay, so the tangent line, dy dx, is perpendicular to a line through xy with this slope. Perpendicular means it has the negative reciprocal slope. So I'm going to take my tangent line slope and say that it's perpendicular to this given slope, which means I need to do the negative reciprocal. So I'm going to say dy dx is equal to positive 3x squared over 2y. Right? The negative reciprocal of this provided slope. Okay, now separate the variables. So 2y dy equals 3x squared dx. Integrate both sides. Y squared equals x cubed plus c. And then they tell us that the line has to pass through, the curve has to pass through 1, negative 1. So I'm going to use that in order to find my line, or my curve. So x equals 1, y equals negative 1. All right, so there is my setup of the equation. So then I get that 1 equals 1 plus c, and hence c must be equal to 0. And so now our solution appears to be y squared equals x cubed. Okay. Now, last step of the problem says that it does wish for us to solve for y equals f of x, so I have to isolate the y. When I isolate the y, that means taking a square root, which means that y could be equal to either plus or minus the square root of x cubed. So which one do we want? Well, notice again, when we stick in 1, we're supposed to get negative of 1 as an output. So since the square root indicates the principal root, we are going to ignore the positive and give our final answer as y equals f of x, which is equal to the opposite of the square root of x cubed.